Have you ever just stopped and wondered why AI seemed to explode out of nowhere? I mean, for years, progress was kind of steady. And then, boom, a full-blown revolution. Well, the reason isn't just about faster computers or bigger data sets. It's about a really fundamental shift in how AI models actually work. So today, we're going to break down why one specific design, the transformer, completely changed the game and unlocked massive scale, while everything that came before it just hit a dead end.
All right, here's how we're going to tackle this. First, we'll look at a simple, real-world problem. Then we'll see how that same problem trapped early AI for years. And finally, we'll uncover the brilliant structural change that unleashed all the power behind the AI we see today.
To really get our heads around this massive shift in AI, we don't need to start with any complex code or math. Nope. We can start with something much simpler, something we've all seen before, a good old-fashioned bottleneck at the office. So picture this. A bank has a mountain of 1,000 forms that have to be verified by 5 p.m. In setup A, you've got one super efficient clerk, just working their way through the pile, one by one. It's a long, sequential grind. Now look at setup B. Here, you have 100 clerks. They don't wait for each other. They just grab a small stack and get to work, all at the same time, in parallel. It's pretty obvious which setup is going to finish first, right?
Now, here is the absolute key to this whole thing. All the clerks are equally good at their job. The 100 clerks aren't any smarter than the single clerk. The huge jump in speed doesn't come from having better workers. It comes from having a better system. The difference isn't intelligence, it's all about the structure. Just burn that idea into your brain.
Okay, so let's take that exact same idea and map it onto the world of AI. Because, before 2017, almost every advanced language AI was stuck working just like that one lonely clerk, plodding along by itself.
Back then, the main type of model was called a recurrent neural network, or an RNN. And the name kind of gives it away, right? Recurrent. It did things over and over, in a sequence. To understand a sentence, it had to read the first word. Think about it. Then read the second word. Think about that one. And so on. It was fundamentally a one-by-one process. And what's the one thing you see over and over again here? Waiting. The model literally could not start processing the second word until it was completely finished with the first. It couldn't touch the third word until the second was done. Every single step depended on the last one, which meant the whole system spent most of its time just waiting in line.
And look, this wasn't just some small inefficiency. It was the fundamental problem. The very people who created the transformer architecture pointed this out in their famous 2017 paper. They said this inherently sequential nature precludes parallelization, which is just a fancy way of saying this one-by-one structure makes it impossible to work like our 100 bank clerk.
So this led to a really weird situation. By that time, we had these incredibly powerful computer chips, GPUs, that were specifically built to do tons of things in parallel. But the AI models themselves just couldn't use that power. It was like having a Ferrari engine, but you can only feed it gas through a tiny coffee stir. The machine was incredibly powerful, but the whole flow was blocked.
So that leads to a pretty logical question, right? If the hardware was getting so much better, why couldn't researchers just sort of brute force the problem with more raw power? I mean, why not just throw more and more GPUs at it? If one computer is slow, then 100 computers must be faster. It seems obvious. But with that old architecture, the answer was, surprisingly, no.
And this analogy just explains it perfectly. Trying to speed up a sequential problem by adding more computers is like trying to fix a traffic jam on a one-lane road by shoving more cars onto it. It doesn't help. The problem isn't the number of cars, it's the single lane.
So, what you had was a total bottleneck baked into the system's design. Because every step had to wait for the one before it, there was a hard-coded speed limit. And throwing more hardware at it didn't change a thing. It just meant you had more expensive, powerful computer chips sitting around doing nothing, just waiting for their turn. This is why scaling was failing. And this is where the revolution really begins. A new architecture came along that didn't just try to make the one clerk work a little faster. No, it completely redesigned the entire office.
That new design was the transformer. And its true genius was what it got rid of. It just completely threw out that one-by-one sequential process. Instead, it used this clever mechanism that let the model look at every single word in a sentence at the exact same moment and figure out how they all related to each other in one shot.
I mean, just look at the difference. It's night and day. The old way, process data one by one, transformers do it all at once. Hardware went from being blocked and basically wasted to flowing and being totally saturated. The waiting problem was just gone. For the very first time, the only real limit was how much computer power you could throw at the problem.
And that right there is the big aha moment. The transformers was the key that finally fit the lock of modern computers. All that immense parallel power inside our GPUs, which had been just sitting there bored, could finally be let loose on language. That traffic jam on the one-lane road was instantly cleared, because transformers basically built a 100-lane superhighway.
And you can imagine, unlocking all that parallel power didn't just make things a little bit faster. Oh no. It completely changed the entire future of AI and kicked off the explosive growth we're seeing right now.
Suddenly, these ideas called the scaling laws became a really big deal. Researchers found this predictable pattern. If you make the AI model bigger, feed it way more data, and use more computers, its performance just keeps getting better. Now, before transformers, this was mostly just a cool theory, because that sequential bottleneck made it impossible to actually do it at any real scale. But once the floodgates were open, the results were immediate and just dramatic. A year after the transformer paper, Google's BERT model completely changed the field. 2 years after that, GPT-3 came along and showed that if you scale these things to be absolutely enormous, they start doing things nobody ever explicitly programmed them to do. The massive models we have today literally could not exist without this one architectural change.
So let's be crystal clear on this. The idea that bigger is better was not new, but that idea was totally useless until the transformer came along. Think of it like this. More data and more computers were the fuel, for sure, but the parallel architecture of the transformer was the first engine that could actually burn all that fuel.
All right, so let's run through the core idea one last time just to make sure it sticks. The big secret behind modern AI isn't some kind of magic. It's a really simple, elegant lesson in system design.
The old models, they were stuck working one step at a time. This created a huge bottleneck that forced our incredibly powerful computers to just sit around and wait, wasting all that amazing potential. Transformers blew that wide open by processing everything together, in parallel. And that one shift, that move to parallelism, unlocked the incredible scale we see all around us today.
So, if you take away just one thing from all this, let it be this. The AI revolution didn't happen because we stumbled on some smarter kind of intelligence. It happened because someone finally designed an architecture that was built for the parallel world we live in. Transformers didn't win because they were smarter. They won because they stopped waiting.